Welcome to this presentation on Monte Carlo simulation as statistical methods of asset valuation. I am Aninda Datta, the presenter. Jai Guruji, Shukrana Guruji. The steps involved in the whole process, suitability, advantages and limitations. The broad steps involved in Monte Carlo asset valuation process. The commonly used available software platforms to perform Monte Carlo. Various advantages and challenges of implementing Monte Carlo asset valuation. Benefits and challenges in using Monte Carlo in product costing. The process of assigning distributions to various uncertain input variables. The insight provided by cost distribution and necessary action areas. The various features of Monte Carlo simulation software platforms like identifying the main input variables, driving output variation, goal seek, visualization, etc. The process of optimization of output distribution by changing parameter of an input variable distribution. The main reasons why Monte Carlo is used more commonly than other statistical methods in asset valuation. The following are the steps involved in the process of using Monte Carlo simulation for asset valuation by the discounted cash flow method. DCF structure modeling, preparing the entire spreadsheet-based structure that calculates final DCF value from various input values generally could be easily done in Excel. Preparing probabilistic distributions for uncertain inputs like project cost, material price, sales price of the finished goods. This could be done broadly by converting the historical data set, example historical prices, costs, etc., directly to a distribution type with relevant parameters. Taking expert advice and choose a specific kind of distribution and the parameters. Monte Carlo simulation engine. The following are the functions performed by the software. Input sampling, raw random values from the uncertain input variables based on the defined probability distributions, example normal, triangular, etc. Scenario generation, feeds them into the model, that is combines various sampled input values to form a scenario, that is one possible scenario of future cash inflows. Model execution and repetition, calculates the resulting output value, for example the net present value or DCF for that scenario, and stores the results. Statistical aggregation, analyze results to compute mean, median, percentile, standard deviation, probability of loss, etc. Visualization and interpretation, create histograms, cumulative distribution functions, tornado charts to visualize valuation uncertainty and sensitivity to key inputs. There are some top software platforms that support all the steps in one environment. Software platforms and their capabilities. @risk by Palasite. An Excel add-in has full-featured Monte Carlo tool inside, defines inputs as probability distributions, calculates DCF as Excel formulas, generates full simulation outputs, stats and visuals. Persons suitable for. Low-code platform provides Excel integrated solutions best suited for finance professionals. Useful for obtaining probabilistic values of uncertain outputs like asset values, project cost, product cost, etc. Model risk by WOS software, similar to @risk but with more advanced distribution modeling. Fully embedded in Excel, used for asset valuation, risk modeling, insurance, etc. More suitable for advanced risk modelers who prefer Excel interface but need complex logic. Oracle Crystal Ball by Oracle/Hyperion, an Excel plugin for Monte Carlo simulation used for asset valuation, risk analysis, financial modeling. Integrates well with enterprise data, especially data of Oracle in ERP. Example, it could fetch deterministic cost of manufactured product from ERP, and on top of that could use Monte Carlo simulation to find probabilistic cost of product. Python with Jupyter plus different libraries are required. However, one single library cannot execute the entire process, so a combination of libraries is required. For executing Monte Carlo simulation in Python or R, a team with coding capability is required. Also, there is no graphical interface, so not much beneficial for finance professionals. For Monte Carlo asset valuation in a graphical and user-friendly way, @risk, Excel, model risk, and Goldsmith Visual Powerful are the best options. Adapting Monte Carlo simulation for finding the cost of a manufactured product brings several benefits and challenges, especially when compared to traditional deterministic costing methods used in ERPs. Benefits of Monte Carlo simulation in product costing: captures uncertainty, reflects real-world variability in input cost. Example, raw materials, labor, energy, overheads, instead of assuming fixed values. Produces a distribution of cost, provides a range of possible costs and probabilities. Example, 90% chance cost stays under $120, not just a point estimate. A better risk estimate helps identify cost risk drivers, scenarios of cost overrun, and downside risk for pricing or margin planning. Supports decision making, enables risk-informed pricing, supply selection, and make or buy decisions by simulating model outcomes. Visual and communicative. Clear visualization of cost uncertainty helps communicate with finance, operations, and management. Challenges of Monte Carlo simulation in product costing. Data requirements. Requires reliable historical data or expert judgment to define input distributions. Example, mean, variance, type, etc. Plus the input variables which are to be represented with distributions need to be selected carefully. Modeling complexity. Building a simulation model for manufacturing cost can be complex and time consuming. Like if the basic financial model has errors, then those errors flow to the simulation result. Interpretation difficulty. Output is a distribution. Users must understand percentiles, confidence intervals, not just a single number. Integration with ERP. Most ERPs are deterministic. Integrating probabilistic simulations into ERP costing modules may require custom development. Computation time. Large simulations with many variables and iterations could be computationally intensive. The flowchart for Monte Carlo simulation for product cost. Monte Carlo simulation for calculating cost of copper-based auto components. Identify input distributions, define cost calculations, generate random inputs, calculate cost, store result, repeat simulation, analyze results. Every input variable should not be represented as distribution, as that would make the calculation very complex. Only those input variables which are significant and have moderate to high variation should be represented by distributions. The basic financial model prepared on a spreadsheet should be correct. Otherwise, there would be errors in the final output variable distribution. Final product cost output variable is calculated many times, called iterations, for many combinations of all the input variables defined as distributions. The output variable results of all iterations are stored in the form of a distribution. Prepare various graphic reports of the output variable. Now, the Monte Carlo simulation product costing is most beneficial in the following areas. New product costing with high uncertainty, multi-stage or high variability production process, cost planning under volatile input prices, budgeting and quoting in contract manufacturing. Example, a supplier of auto components manufacturers for an OEM. Each unit of manufactured product has complex production steps by casting, machining, heat treatment, etc. Costs vary due to fluctuations in raw material prices, process yield, labor rate, reworking. The steps involved in Monte Carlo simulation and product cost are: identify main cost drivers, raw material price, example aluminum price, steel price, etc. Machine time cost varies with part complexity, wear, downtime, etc. Labor cost affected by overtime, learning curves, etc. Scrap rework rate depends on casting defects, dimensional deviations, etc. Energy consumption fluctuates with process variation. Overhead allocation based on certain production volumes, changes in the overhead cost. The use of cost distribution in different areas and distribution of the final cost. Define the input distribution. Based on historical data, the platform itself could suggest a parametric distribution and the relevant parameters from its distribution library, or the distribution could be defined by an expert. Aluminum price, say a triangular distribution with parameters such as minimum, maximum, and model price. Rework rate, say a beta distribution with parameters as mean and standard deviation. Machine downtime, say exponential, Poisson, or uniform. Number of hours per batch. Labor efficiency, say triangular. Run Monte Carlo simulation. Suppose 10,000 iterations. For each run, samples all input variables, computes total cost per unit. Result, probability distribution of total unit cost, not just the average cost, the standard deviation of cost, the confidence intervals of the costs, etc. So a company could quote price based on the cost associated with a specific confidence interval. The insights provided by Monte Carlo and necessary actions. So this is the probability density function of the costs. So this is the 10th percentile. So this is the mean, and this is the 99th percentile. This is the 98th percentile. This is the 88th percentile. This is the 75th percentile. The mean is $81.32, $31. 10th percentile is $69. 75th percentile is $88. 88th percentile is $90. 90th percentile is $94. 99th is $103. As confidence level indicates what is the probability of achieving a cost level or less, a company chooses a confidence level for the decision making. Suppose a company is conservative, then it may quote price based on the cost appearing at 90th percentile. Suppose the buyer company disagrees and wants to pay based on the cost of $90, that is based on 80th percentile. Then the manufacturer should keep provisions for price hike in the contract. So a company needs to set the standard cost at $90. The COGS would be booked at $90. The manufacturer should also make provisions for adverse manufacturing variance for 94 minus 90, that is between the 90th percentile and the 80th percentile. An aggressive company may quote price based on mean cost of $81, but may insist on liberal price hike provisions in the sales contract and make necessary provisions for adverse manufacturing variance, as COGS needs to be booked at $81. The following features are provided by the platform enabling Monte Carlo asset valuation. It identifies the main drivers of variation in the probability distribution of outcome, which is the DCF, discounted cash flow. It is like doing a sensitivity analysis of the probability distribution of DCF oblique IRR. Generally, those input variables drive variance in the outcome which have substantial value as proportion of DCF value. Variables themselves have large variance. Example, the wide distribution have early impact on cash flows like COGS, that is cost of goods sold, land acquisition for projects, etc. Repeated impact on cash flows have multiple period impact like sales growth. As spreadsheets provide a goal-seek feature whereby a target value for an output variable is determined by making necessary changes in the value of a chosen input variable. Similar goal-seek feature is available in Monte Carlo software, whereby a target parameter value for output distribution is obtained by making necessary changes in parameter value of a chosen input distribution. So a specific value of a standard deviation of output variable could be obtained by adjusting the standard deviation of an input variable, to be done by the Monte Carlo simulation software. The contributors to variance in output distribution are found by calculating the difference between median input value for all iterations minus the median input value for the relevant iterations. Suppose the mean discounted cash flow is 2 millions with standard deviation of 0.3 millions. The DCF value at 98th percentile is 2.38 millions. The various input distributions driving the DCF distributions are revenue growth, driving rate, and EBITDA margin. Suppose this is the ranking of the various input variables driving the driving the variance in the output distributions. The top rank is the revenue growth rate, second is discount rate, third is EBITDA margin. Now you want to know what are the major input variables driving the change in output value by 0.38 million. Suppose the DCF distribution is computed by taking the 5,000 iterations, so the 90th percentile value is calculated from the top 50 iterations, it is the top 10%. At the rate risk calculates it the following way: finds median value of all input distributions for all the 5,000 iterations, suppose it is M1. Finds median value of all input distributions for those 50 iterations, suppose M2. The value M2 minus M1 is divided by standard deviation of the respective distributions for all iterations. That is the difference expressed in terms of number of standard deviations. The input variables are ranked in descending order of the values calculated above. The input variables having higher values are the higher drivers of variance in. The output distribution could be optimized by maximizing or minimizing a distribution parameter or value for a specific percentile. As in Excel, the solver function could maximize or minimize a linear equation subject to some constraints. Example, maximize the profit given by a linear equation subject to constraints like minimum sales quantity for each SKU, total production volume less than a certain value. In linear equation, the output and input are both point values. So the maximum values or minimum value of output is obtained by changing an input value or decision variable. In Monte Carlo simulation, the output variable and input variables are both distribution. So the output variable is optimized by maximizing or minimizing a parameter like standard deviation, the value of a certain percentile of the output distribution. This is achieved by changing a parameter of the input variable distribution, the decision variable like mean, standard deviation, or changing the shape of the input variable distribution by the risk management steps. Example, a highly conservative company is interested in maximizing DCF value of the first 40th percentile, that is a 60% probability of achieving, by changing the raw material price variable. It could be done by reducing the standard deviation of the distribution, which in turn could be achieved by hedging the raw material purchase through a long haul options. However, a long haul option is an associated cost but caps the maximum price. So the higher side of raw material price distribution is bound to be curtailed, but the distribution shifts right by cost of the call option, thus reducing the achievable maximum DCF for higher percentiles like 88th percentile and above. An aggressive company may try to maximize DCF value of the 75th percentile. If optimization is done by risk management, then lifting the lower end of the distribution will cause a decrease in higher end of the distribution. That is, the shape of the output distribution changes. The input variables which drive the major variation in the output variable distribution are more effective decision variables for optimizing the output variable better. If the DCF distribution shifts entirely rightwards, then it is not exactly optimization but is cost reduction. If the output distribution of DCF is optimized by managing risk or volatility, then the output distribution does not shift rightwards but shape of the distribution changes. Suppose a copper components producer buys copper. The copper price follows a log normal distribution with a mean of 12 per kg and standard deviation of the 20% depicted in the first graph. Suppose the buyer buys a call option with strike price of $15 per kg. The distribution is depicted in the second graph. Now the first graph shows the log normal distribution of copper price. Now the second distribution shows the log normal distribution of the copper price with a call option at a strike price of $15. That's why the right side of the distribution is curtailed at $15. The left hand extends fully so that the company could derive full benefits of the fall in the copper price. As in the second graph, the maximum price is $15. The resulting distribution will experience an increase in DCF values of the lower percentiles. However, there is a call option cost, so the mean profit of DCF distribution will shift leftwards by $2 per kg of copper processed. So this is the DCF distribution when there is no call option on the copper and the mean copper price is $12. This follows a normal distribution with a mean DCF of $30. And this is the DCF distribution when there is a call option on the copper price and the call option is at $15, so that the left hand side of the DCF distribution is truncated at $23. However, since the company derives full benefits of the fall in the copper price, so this DCF distribution extends fully towards the right hand side. There is only one uncertain input variable that drives DCF distribution, that is the copper price. On buying the copper call option, the lower percentile of DCF distribution is curtailed at $23, so optimized for the lower percentiles. Now for shifting the output distribution leftwards or rightwards, the mean of the distribution of decision variable should change. Most optimizations are done by changing the shape of input variable distribution. So generally optimizations are not win-win scenario, but aimed at changing the shape of the output distribution. Suppose a company de-risks its overhead expense by opting for more fixed costs. Then the company gains during high volume but losses during the volume decline. As this is de-risking, this will change the shape of the DCF distribution curve by increasing the DCF of higher percentile and reducing DCF of low percentiles. The DCF curve will shift right only if the actual reduction of overhead expense happens. If the price of raw material is reduced, then the price distribution shifts leftwards. So the DCF distribution shifts rightwards with shape remaining the same. Monte Carlo simulation is the most widely used statistical method for asset valuation because it offers a powerful, flexible, and intuitive way to handle the uncertainty and complexity in financial models. If you are comparing to Bayesian methods, regression models, or closed-form financial models, Monte Carlo stands out for its versatility and intuitive logic across asset types and risk environments. Monte Carlo supports a wide range of probabilistic decision making like probability of loss or gain, value at risk, expected shortfall, tail risks. All these make it very useful for valuing risky assets as values cannot be accurately predicted with a mathematical model. So this ends this episode. Thanks for watching. More aspects of use of statistics and asset valuation will be covered in the subsequent episodes. Jai Guruji, Shukrana Guruji.